Hello, everyone. So, welcome. So we are going to continue our lecture on virtual memory. And we are going to start discussion on caching and TLBs, which stand for translation look-aside buffers. So if you recall, address translation, as a name implies, it's about translating the addresses which are viewed by the application, by the CPUs, into physical addresses. And there are a couple of reasons why we want to have these different kind of addresses for the application and versus the physical addresses. And some of them are about providing the illusion to each application. It has its own machine, its own resources, including the memory, which means that then you need to map the address space of each of the application in the same physical space, which is physical memory. And also another reason is protection, because you want to protect the address space and of one application from another. And also sharing, controlled sharing, if you remember, in which actually some parts of the address space you want to be shared. For instance, the address space which contains a code of a shared library, which is a code of a library which is used by two applications, like Windows library on your own Windows machine. You do not want to replicate that code in each application. You want to share that code. Okay. And typically, you do the sharing. It happens, it's handled by one of these components, a chip, which is called, or it's memory management unit. So this was originally was a standalone chip, which was you put near between the processor and the memory. But of course, in the more modern processors, it's just a component on that processor. And one of the one of the techniques to do address translation was a segment. We're using multi-segment model. And in this case, if you remember, each segment is represented by a base and a limit. Okay. And now the virtual address, virtual address is again, it's the address which is seen by the CPU and is seen by the application, is split into two. The first part, the first few bits, represent an index in the segment table. And then there is an offset. Okay. So when you have a virtual address, you look at the first field, which is the segment number. The first bit will represent the segment number. You use that to index into segment table, and then in that segment table, you are going to find the base of the segment and the limit, and you are going to compute the physical address by adding the offset, which is the second field in the virtual address, to the base, the segment base. Okay, this is how you get physical address. And of course, you are also going to check whether the address is generated is less than the limit. So it's within the segment. You also have, in some architecture, actually in Intel x86, instead of having the first, the bits in the address, in the virtual address representing the base, indexing into the segment table, you have just a bunch of segments. Initially you have 4 segments, and these segments are base segments are stored in special registers like ES. This is S is for the stack, and 3 other registers. Okay. And then you compute the address by taking the virtual address and you are going to add it to the, the, the segment register. And that's how you are going to compute the physical address. Finally, there is a bit, valid or not valid. And this is one use of this one is that a segment, not all segments of all application can fit in the physical memory at the same time. So when you run out of space in the physical memory and you want to load, you start a new application, a new program that you need to allocate space in the physical memory to that new program, to the segments of the new program. You may take one of the existing segments of an application which doesn't run, and you are going to store it on the disk. Okay, and so then therefore the segment is no longer in memory. So then you can say it's not, you can use this bit to specify that. So whenever next time when you are looking for something in that segment, then you are going to, you are going to get an exception, and the exception is going to be treated by the operating system, and the operating system will bring the segment from the disk to memory before executing that instruction. Okay. So this is some examples. Okay, so here it's a simple, an example of an architecture with 4 segments. The address is 16 bits. The first 2 bits of the address are used to specify the segment number. And because we have 4 segments, we need only 2 bits. So these are bits 15 and 14. And the rest of bits from 13 to 0 represent the offset. On the left-hand side, you can see the address space, the virtual address space. So as seen by the processor, by the application. And we have our traditional 4 segments, the code segments, the data, the stack segments, and this is also, we added a shared segment. Think about this is either the data or the code which you may want to share with another application. So here in green, you have the table, the segment table. Again, 4 entries for code, data, shared, and the stack. And you see you have the base and the limit for each of these segments. So now, let's see what happens. So for instance, and on the right-hand side, you have the physical address. For simplicity, in this case, the physical address and the virtual address spaces, they have the same size. Okay, so say you are going from the code, you are going to execute the instruction in the code segment. And so where is that going to be mapped in the physical address space? Well, if you look about in the segment table, because the first 2 bits of everything in the code segment are 0. So therefore you are going to identify the first entry, right, in the segment table. And you have a base of 4,000 in hexadecimal format. So therefore you have to add an 4,000 to every address, a virtual address in the code segment, and to get the corresponding physical address for the code in the physical address space. Okay. Then for data, the data starts in the virtual address space at 4,000. This means that what are the first 2 bits of any address in the data segment? Why don't you tell me? It should be a very simple answer here. So the first, you have 16 bits. When we use a hexadecimal representation, right, 4 bits represent 1 digit. So now we have 4 here first. What does it mean? What are the first 4 bits? The 4 bits representing the 4. How do you write 4 in binary representation? Okay, so here it is. I'm writing this in our chat. So for in binary representation, if you want to represent it um, using 4 bits, it's what? 0, 1, 0, 0, right? This is it, right? It's 1, 0, 0 is 4 in the binary representation, which means that the first 2 bits for any address in the data segments are what? The segment number here is what? 0, 1. Now it's not 0, 0, 1, it's 0, 1 because it's only the first bits. But it's correct, you know, it can move. Okay, so it's 0, 1, which is equal to 1. Okay, this is what you have, right? So therefore, to translate any address in the data segment, what do you need to do? You go to the second entry in the segment table, the one which the segment ID number is 1. And the base here is 4800. So what you need to do is that you are going to add, in order to translate any address in the data segment, you need to add to it 4800. Okay. And for the shared segment, this, you know, the things go similarly. For the shared segment, they start at 8,000. So the first 4 bits is 8, represent 8. What is a binary representation of 8? It's exactly. So the first 2 bits are 1, 0. So the segment number, it's 1, 0 is 2, right? Because you take only the first 2 bits. And finally, stack C. What is a C? The representation, binary representation of C. You should remember this, right? You should review. It's 1, 1, 0, 0. It's exact. Very good, right? So the first 2 bits are 1, 1. So it's 3, number 3. So of course, it's the last entry in the table. And for to the stack, the base is 0, right? So you add the base, the offset to the base. So we started from 0, 0, 0. Okay, does it make sense? Okay, let's look at this other example. By the way, you should you should try. These are some very important slides, because you may expect not only to understand how the address translation works, which is one of the fundamental mechanisms used by in today's processors, leveraged by the operating system to provide virtual memory abstraction, but also because you can expect problems like this in your next midterm. Okay. So now let's look at this piece of code and see what happens under the hood. And we are assuming this piece of code is going to run on the previous architecture from I just showed you in the last slide. Okay, so you have the segment table is the same. And now is the code. So the code starts the 240, right? So so basically the entire address is 0240, but you don't show the first 4 bits, which are 0, right? Okay, so now let's see what happens. And this is a pseudo assembly language code. And let's see what happens when we start to execute this code. The first instruction is a main. And basically what this instruction is doing, it loads an address, which is bar X, into register A0, right? Now, this code, it's run in the user process. The user process see virtual addresses. So all the addresses you see here are virtual addresses, okay? But now the code and the data, they are actually stored in the physical memory. So in order to read the instructions and access the data, we need to translate the virtual addresses to the physical addresses. Okay. So the address, the instruction, first we need to fetch the instruction. In order to execute the instruction again is in physical memory. So the address, the virtual address, it's 0240 like we discussed. And here it's a binary representation of the address. So the first two bits are 0. So the segment ID, the segment number, is 0. So therefore, in order to translate this address, virtual address 240 to a physical address, we need to add the base address corresponding to the segment. So the base is 4000 and the virtual offset, right, is 240, right? The virtual offset. The offset is these are the black bits in the address. The bits encoding the segment identifier are the green bits, obviously. Okay. So you have to add all the offset, which is 240 to 4000, which is a base, and therefore you are going to get the physical address 4240. And now you are going to use this address to fetch the instruction from the memory. And the instruction is basically, like I told you, is to load the address, which is bar_x address, which is 4050. This is the virtual address, into register A0. Okay. Now, after that, you execute those instructions, you would know very well what happens. Next, the program counter, it's incremented by 4, right? Because here, assuming that there are instructions, they occupy 4 bytes. Okay, the next instruction address is 244. Okay. So let's execute the next instruction. It's again, in the next instruction, you are going to see, you have now the address is 244, like I mentioned. The physical, if you look at this will also be in the code segment. So you need to add the base, which is 4000. The physical address will be 4244. And you are going to get the next instruction, which is JAL, to jump to this stringlen address label, right? And this is exactly what you do it. So, but before jumping, here we store the return address. So after we execute the function stringlen, we need to return where? To the next instruction after the jump. The next instruction after the jump will be 0x248. Okay. So therefore, we are going to, we assume here that we have a return address registers, which stores the return address. So we are going to load into the return address 0248. And this is done automatically by the compiled code by your application. And then you move in the program counter the address where you want to jump. So the address where you want to jump, the label stringlen is corresponding to the address 360. Okay. So you are going to jump there and you are going to execute that next instruction, which will be the address 360. 360 is again is in the segment code. In order to compute the physical address, you are going to add the base, which is 4000. So 4000 plus 360 is 400, 360. And then you are going to read from the physical memory. You are going to read and this instruction, which basically initializes a count. So put a 0 in a register V0. Okay. And once you execute that, you go to the next instruction. And the next instruction, it's at the address 364. And this next instruction, it loads what is at this particular address, which is stored in A0. So remember that what is stored in the A0, it was var X address. So this var X address is 4050. So now we are want to load in register T0 the content of the address var X, so of the address 4050. Okay. So when we want to do that and we want to access it, to see what is the content at that virtual address. The virtual address is 4050, and this is a binary representation. The first 2 bits are 0, 1. So the segment index, which corresponds to this address, is 1. And therefore, the base address of that segment is 4800. So therefore, you need to add the 4800 to what? To the offset. So what is the offset here? The offset here, notice, is 50. So the virtual address is 4050. Okay, but remember, the first 2 bits of this address represent the segment ID. That's 1. And the last, in this case, 14 bits represents the offset. But the last 14 bits is 50. So now the offset is 50. It's again, offset is a black digits, right? 0 or 1. Okay, so then you are going to add the offset to the base, which is 4800. So the physical address you are going to compute is 4850. And you are going to load the byte from that address to T0. And you increment the program count. So the main thing to note here that everything which is in what the processor sees, everything what is in the registers of the processors, all these are virtual addresses. The translation happens only where you are going to access the memory. So the memory management units really sits between the arithmetic logical units and all the registers and the memory. Okay? Any questions? Okay, we spent quite a bit of time on this one, but this is important. Please make sure that you understand this example. Okay? As you'll see from the previous years and previous exams, you know, you are going to see a lot of problems like this one. So a few things about segmentation. The one problem with the segmentation, you know, it's nice, it's a very elegant solution, but you are going to translate on every instruction, everything, you know, even you fetch an instruction, access a, you know, read some data, write some data from the memory. And virtual address space has holes, right? Because you are not going to use everything in the in your virtual address. So and that's why you use a segmentation in the first part, in the first thing, in the first place. Because if you think about, if you have the code and the segment grows, you put the segment as a high addresses because it grows to the smaller, grows downwards to the smaller addresses. And for instance, the data segment, you have to be as the lower addresses because it's growing up, okay? Whilst the stack growing down. So you need to separate them, and between them, there is a gap, right? So if you have segments, if you don't have the gap, if you don't have the segments, that gap will occupy space in the physical memory. Space could have been used, empty space could have been used to allocate to other processes, other applications. However, if I have these 2 segments now, each segment can have One segment can have data, one segment can have the stack, and then they are going to be mapped on the physical memory, and the gap, I don't need to map it. I don't need to just waste the space from the physical memory. So now, the one thing to notice here is I said, okay, you allocate segments for the stack and the data, but if allocate and how allocate, the stack has a certain size and allocate that physical memory for the stack at that given size, what happens when the stack grows? And that stack grows because as I call more functions, or say recursive programs, every call puts the arguments and puts the return values and so forth on the stack. Okay, so how do I do that? Well, in that sense that when I'm going to grow the stack, for instance, then I'm going to access an address outside the limit, and that will generate an exception. The exception will be treated by the operating system, which is going to grow the stack. Okay, grow the limit, or modify the base and provide more room now, so the program can put more things on the stack. The same thing for the heap. Okay, there is a question here. Why did we not translate varx in the first line on the previous slide? So that's a very good question. Why didn't translate varx? Remember what I said? Everything is in the registers is virtual addresses. These are all virtual addresses, because the rule is that the addresses are only translated when I am going to access the memory. In this case, I am not accessing the memory. Varx is just a virtual address, right? I don't need to access the memory for that. When I need to access the memory is when I'm going to read the content as that virtual address. And then I need to find the corresponding physical address. And then on I do translation. But everything what is in the process, in the registers, it's their virtual addresses, basically. Okay. Of course, you need to protect the segment table. Only the operating system has to be able to modify it. And also it provides, the operating system provides protections for different segments, for instance, to make the code segment being read-only. Okay. Now, let's say we do a context switching now. What do we need to save and restore on context switching when you have a process context switching? So besides, as you know, that we need to, to save a bunch of things like file identifiers and things like that. The other thing we need to store now is a segment table, because the segment table, as I shown you in the previous slide, in the previous example, you have one segment table per virtual address space, and you have one virtual address space per process or per application, right? So when you context switch a process, you have also to save the segment table, because the next process is going to run is going to have its own segment table. Also, like I mentioned earlier on, some of the segments of the process which is which is no longer running can be stored on the disk in order to make room for the segments of the next process being run. This is what happens, is that again, if not all segments fit in memory, you save them on the disk and you swap them. So basically, the P1, say process P1, we switch from process P1 to P2, then we can save the segment of process P1 on the disk to make room for the segment of process P2 to be brought in the memory. Of course, if you have to do that, the context switch cost will grow dramatically. Okay? So you need to be very careful about what you switch off or what you swap out and swap in, because you really want to minimize the operation on the disk. And we are going to learn about that the next couple of lectures. Problem with fragmentation. Problems with segmentation. One of the biggest problem is fragmentation, because now you need to store different. You need to be able to store and to fit segments of different sizes in memory. And if you remember the last lecture, we had an example in which you leave a lot of gaps, and you can get to a point in which you have many gaps in the physical memory, but none of the gaps can be big enough to store a new segment, to store a new segment, despite the fact that if you add up all the gaps, it's much more than what is needed by that segment, right? Think about, you have 100 gaps, each gap is 1 gigabyte, and you have 100 gigabytes in total of available memory, but now you have one segment which requires 2 gigabytes. So you have plenty of available space, but none of the available spaces, contiguous spaces, is large enough to store that segment, 2 gigabyte segment. So what you do that, you can take one of the segments which are there to addition to one of these 1 gigabyte gap, and you are going to store on the disk. You are swapping out to make more room, or you can move segments around. Okay. So there are two kinds of fragmentations, both of them waste space. Internal fragmentation, you don't need all the memory within allocated chunks, and this is also and then external, which is free gaps between allocated chunks. So what in the example I mentioned to you, I was talking about the external fragmentation. Okay. And next we are going to talk also about internal fragmentation. Okay. So basically this is about, another view about the general, how the address translation happens. This providing a little more intuition by showing two virtual address spaces mapped to the same physical address space. Okay. And these programs 1 and programs 2, or this process 1 and process 2, the virtual address spaces to each of them can look absolutely identical. Think about, you run the same application, 2 instances of the same application. Okay. But of course, the translation, while in the virtual spaces are identical, you have in both virtual spaces the same thing as the same addresses, virtual addresses. When you are going to map these virtual addresses to the physical address space, when you are going to translate them, you are going to translate in such a way that they are not going to conflict. So now with segmentation, we have this with external fragmentation. And it's sometimes it's harder to allocate storage to variable size chunks. So there is a solution for that. And a solution for that, which is very simple, it's about, instead of allocating variable size chunks, you allocate fixed size chunks. And these are called pages. So every chunk of physical memory is equivalent in the same that it has the same size. And this can allow you to simplify a lot of things. For instance, how do you handle allocation? So one way to handle the allocation is to have a bit vector, and each bit in the vector represent one page, and the value 0 is that whether that page has been allocated from the physical memory, or and 1 if it was allocated. So if you want to find a page in physical memory you can allocate, you just find a 0 in this bit vector. Okay. Now, what about the size of the pages? If the pages are too large, again, all pages have the same size. What is the problem? What is the problem if the pages are too large? Wasted space, internal fragmentation. Excellent. So I by Git and Ellison and cost of context switching can be higher if you need to swap that page out. Right, that's correct. But yes, the main thing is about internal fragmentation, because if you think about, if you have these pages, say you have a page of 1 gigabyte, if your program is only one megabyte, you waste most of the space. So you want small pages, okay? The problem with the small pages, what is the problem with the small pages? Any guess? Lots of accounting, more translation. It's yes. Lots of accounting. I wouldn't say more translations and larger page table. Okay, you already know about it. Yes, but it's accounting is harder, right? It's you have to deal with more things, right? And okay, so let's see. So now, how do you do the translation? But there are not many more translation because in theory, right? Because you still need to, every virtual address you need to translate to a physical address. The little bit of truth of that, the higher overhead per translation could be. But the number of translation is basically the same. Yeah, Warsaw cache can be that as well. Yeah. Okay, so how is a translation works with paging? It's very similar with segmentation, but with a few differences. So first of all, you have a page table, and the virtual address, as again, is in 2 parts. We have a virtual page number and an offset. But there is a difference. The offset is not added to a base address. The offset of the address remains the same. So with translation, when you use paging, what happens is only the virtual page part, the first field changes, right? A virtual page number is replaced by a physical page number. That's it. So the same like previously, the first bits, in this case, the virtual page number, in the previous case was a segment number, are going to index in the page table. But in the page table, what you are going to find, you have a page number, which is a physical page number. And you are going to take that physical page number and you are going to concatenate to the offset of the virtual address. So the offset of the physical address and the offset of the physical address are the same. Okay. Typical page sizes are between 4 kilobytes and 16 kilobytes, so are quite small. 4 kilobytes means what? 12 bits, you need 12 bits. And 16 kilobytes, you need what? Another 14 bits, right? So if you have even smaller pages, right? And this is where you see the number, the problem is the small pages. So you have a 32 bits address and you are going to use 1 kilobyte pages. So you need 10 bits offset. This is what you need, a 10 bits offset. And therefore the virtual page number, the number of bits there is 22 bits, 32 minus 10, 22 bits. So therefore, the page table will have 4 million entries. Huge. Okay. And just think about if you have 64 bits address. Okay. So in order to do that, for instance, you are also going to not allocate space for the entire, the maximum size page table. So you are going to just grow this page table as you add more pages to it. And therefore, you are going to have, in addition to the page table pointer, which represents the start of the page table, also the page table size, which is, as the name implies, the size of the page table, which can be increased as you add more tables, or as you allocate more pages, and so therefore you allocate more entries. You add more entries to the page table. Also, with each page, you are going to have a bunch of bits, which represents some, we are going to discuss them more a little bit later. So keep in mind about these bits. We are going to give an example a few slides later. So this is a very simple page table. You have a 4 byte space, so it's a trivial example. You have this on the virtual memory, you have 4 pages starting from 0, 4, and 8. And then you have a page table only with 3 entries, right? Because you have 3 pages in the virtual memory. So assume that the address space here has equivalent of 8 bits, so it's 64 bytes. So the address, if you need for the page table, again, if you have 4 bits, you need only 2 bits, right? To represent 4 bytes, to address 4 bytes. So therefore, the last 2 bits represent the offset, and the first 6 bits represent what? Represent the page number. Okay, so if you want A, it's at the address 0 here. So if you want to translate address 0, then the page number identifies the first entry in the table. The first entry in the table contains 4. So now 4 is a new physical page number. So you are going to concatenate this 4 with the offset, which is 0. So you are going to get 0x10. Okay. The same thing, similar things happen if you want to access the first address, the address 4, the virtual address 4. The virtual address 4 now is going to lead you, because the offset is 1, is going to lead you to the second entry in the page table. The second entry in the page table contains 3, so you are going to concatenate 3 with 0, which is the offset. You are going to get to the address 0C, physical address, and so forth. Okay. Any questions? So question here, why was page size chosen between 4 kilobytes and 16 kilobytes? So this is again always it's a trade-off. The smaller the table, the smaller the page, the smaller the internal fragmentation. So the less wasted space. However, the smaller the page, the larger the page tables are. So therefore, it's much more context switching actually can be more expensive. Good question. Okay. And these are some other translation. Translating the address 5, it's going to translate to the address in this case is basically 117, and I think there is another example. 9 is going, sorry, previous case the address 6 was translating to the address 116, and the second case the address 9 is going to translate to address 5. No, physical address 5. So there is an anonymous question asking about if the 0x1234567 is the address, could the first 12345 can be the offset? Now, the offset are the last bits in the address. Okay, so in this particular case, again, the offset, if you look at the first one example here, the offset it's 1 0 are the black bits, and the page number are the red bits. So the offset is 2 in this case, and the page number it's 1. And page number 1 selects the second entry in the page table, which is 3, so it's 1 1. And the offset remains 1 0. So now I have 1 1 1 0, which is basically E. Okay. What about sharing? Well, if you want to share a page between processes, you know, these are pretty easy, right? You have each of the processes has its own page table, and if you want to share the same pages, then the corresponding entries are going to point to the same physical table. That's it. Very elegant. Where is page sharing used? Kernel region of the processes. So for the processes, you have a kernel region, as you remember. So every process has the same, all the processes, they have to see that you are going to share this code, the kernel code, across all the processes, right? Because the same code is not going to change. You can, and by the way, this is protected, right? It's like the kernel will have the process only can access at the user level. When I are talking about the kernel region, I'm not talking about kernel region being accessed by the process. I'm talking about the kernel regions associated with the process, which is accessed by the kernel during the context switching. During different processes running the same binary, right? You don't need to replicate that because the code is read-only. User level libraries, like I mentioned, and or even sharing the data between you. You can share the data between two processes. You can use a share memory. So this is another example. This is a summary of paging. On the left-hand side, you have the virtual memory view. On the right-hand side, you have the physical memory view. And in the middle, you have the page table. You see that many entries in the tables are null, but this is a full page table. And here we are assuming an 8 bits address. And now the offset are the last 3 bits. So the page size is 2 power 3, so it's 8 bytes. And the page number is 5 bits. So you are going to have 2 power 5, you have 32 entries in the page table up to. Okay, so now the one thing, and on the right hand side, you have again like the physical memory. So one thing here I just want to show you, and I showed earlier on, I said that, well, the stack, how the stack and the heap grows here. So now the stack again grows downwards, so grows, going to lower addresses. And you see here the stack, it's on the right hand side, and with what I represented here with the gray, the pages with gray are already allocated. So only the pages which are white are not allocated yet. So let's see what happens and how you are going to grow the stack. So now the problem is that let's say that I want to grow the stack by 2 pages. I decide to grow the stack by 2 pages in the virtual memory. In the virtual memory, I can very conveniently grow the stack because I have enough space in the virtual memory. However, in the physical memory, if I'm going to try to grow it, I can allocate another page. You can allocate another page. Maybe you have only room for another page there if you want to allocate contiguously the pages to the stack. But the point with the page with the translation is that these pages do not need to be allocated contiguously, right? So therefore, the only thing you can do, the only thing you need to do, you need to find room for 2 other pages, and you are going to allocate these pages for the stack. But again, they don't need to be contiguous, right? Whatever is contiguous in the virtual memory doesn't need to be contiguous in the physical memory. Okay. So now the biggest problem and the challenge, the table size, if you in the simplest version, in the simple instantiation, in the simplest implementation, the table size it's equal with the number of pages in the virtual memory, right? And this can be absolutely huge. So let's take an example. So you have 32 bits address space, right? So you have 4 gigabytes virtual address space, and these are just the units for you to remember. So the one thing to remember here, and one confusion I've seen often, is that when you are talking about the memory, we are talking about the power of 2 units. So 1 kilobyte is 10 to power 10. 1 megabyte to power 20. And gigabyte to power 30. When we are talking about bandwidth, and how much capacity, network capacity, we are talking in power of 10. Okay, 1 kilobyte or 1 kilobit, it's 1,000 bits. 1 gigabit represent what? It's 1 billion bits. Okay. So now assume the typical page size is 4 kilobytes. So it's 2 power 10. We need 10 bits to address any byte in a 4 kilobyte page. So therefore, okay. Sorry, we need 12. What I'm talking about. If the page is 4 kilobytes, this means 2 power 12. So therefore, I need 12 bits to address any byte within a page. So the offset is 12 bits. And therefore, if the offset is 12 bits, the page number, it's 32 minus 12 is 20 bits. So now the page table size can have as big as 4 megabytes. Right? Why is 4 megabytes? Because each of the entry in the page table needs to have 20 bits. Okay. And then you are also going to have some other, like you'll see, some other flags associated. So you have 32 bits for each entry. So it's 4 bytes, and you have 2 power 20 entries. So it's 4 megabytes total. So this was a lot of memory. And now think about, this was in the past when you have 32 bits was the standard, but now the standard is 64 bits. There is no way, right? If you try to do the same thing here, you are going to have 30 exabytes, which is only for the page table. Actually, you don't have enough physical memory for that physical to store that the page table. This is really a lot of space. So what is the solution here? Right? And by the way, all this space is empty. Most of this, no, not always. Most of the space is empty because you don't have as many page tables, right? You have very few page tables, right? So, which are actually allocated. So what is so this is a big problem and we are looking out for a solution. So a little bit of a discussion about page table before going forward. So what do you need to switch on the page table? What do you need to when a context switch happens? What do you need to do? You need to have a page for the table point, the page table pointer. So the beginning of the page table and the limit, the size of the page table. Again, remember about the dual mode operation and because these page tables can be only modified and accessed by the kernel. You cannot let an application access these page tables because then they can change the page table and they can point to anywhere to any other address, including the kernel or to of another the address of another applications. And now let's look at the pros and cons. On the pro side, it's a very simple memory allocation. Remember, you have a bit vector is 0 or 1, whether the page is allocated or not in the physical memory. The bit vector contains 1 bit for each page in the physical memory. Easy to share. The cons we've seen. If the address space is very sparse, the page table can be huge. Right? It's again, if the page table is big, then you need also probably to context switch. You cannot keep all the time in the memory. If the process with page, if the tape is a page table of a process, if the process is now switched off and is no longer using the CPU, you may want, it was preempted, you may want to take the page table of that process and swap on the disk. But if that is large, then the overhead is very large. So the TLDR here, the page table, the paging as a technique, it's elegant solution, very simple to implement, provides low internal fragmentation if the pages are small. On the downside, the problem we encounter is when we have is because the page tables can be huge. Okay. So what is the solution? Well, the solution is you repair the same technique, right? Like you recursively do it, and it's multi-level paging, right? Look, if the page tables are very large, then why don't we have a page table for that page table, right? Or you can combine paging with segmentation. Okay. So, and these are the two solutions. Segment mapping, you are going to have segments, and in the segments you are going to have you page the segments, and then in the page tables you are going to page the page tables. And let's look about how this is working. So at the core, remember that the page table is a map between the virtual page number and the physical page number. This is what it is. So a simple page table is just a lookup table. VPN, the virtual page number, it's an index in this table which contains the physical page number. By the way, what other map structures can you think of? There are many of them, trees, hash table, and so forth. But obviously, these are more complicated. More complicated means higher overhead, even though they can have slower storage overhead. The beautiful things about the page table is very quick to access it, right? It's just an index. If you use the trees and hash tables, and we'll see about that, they are much more space efficient. You don't need to maintain all the entries, which, for it, there is no table. But accessing those is much more expensive. That's the trade-off here. So one simple solution is like we mentioned, is to have to the problem of having very big page tables, is to page these page tables. And basically here is a two-level page tables. And here is that instead of now the address has three fields. At the end is the offset, like before, no difference here. But what was previously corresponding to the page number, now you split into two fields, which corresponds to virtual page numbers or page indexes for the two-level pages. Okay, so the first 10 bits in this case represents a virtual P1 index. So in the index in the first level table, page table. And this is going to take you, is going to contain an address to a page containing the page table entries at the second level. Okay. So in order to compute now the entire physical address, use a P1 index to find the address of the page containing the physical page number, which is stored in the second level. And this physical page number is going to be concatenated with the offset like before. And now you have the physical address. Okay. So it's the same thing, The only difference is that now you split the physical page number into a part which is going to index into a page table, first level page table, which contains the address of a second level page table. And the second field in this page number is going to index in this second level page table. And at that entry, corresponding entry, you are going to have physical page number. Right? And you can have many more levels. So now these are some announcements. We are just 15 minutes before the class, so ends. But here are some announcements. We release a midterm scores, and please check Piazza for regrading policies. I think you did quite well. The scores and the distribution is very much in line with that of the past midterms in the recent years. The project 2 design document, remember, is due by at the end of this Friday. And the homework 3 is due on Sunday at the end of the day. So if you want an extra credit point, please feel free the mid-semester survey and check on Piazza for details. Okay, so it's free extra credit. The next lecture, I'll be out of town, and Nathan Pemberton, which is a senior PhD student, which is expert both in architectures and systems, is going to teach this class. He's a fantastic teacher. fun, I really urge you to attend his lecture. They are going to be a lot more fun than my lectures. So he's a great presenter. So I remember that I mentioned to you now that in a page table entry, besides the physical page number, we are going also to have some bits. Okay. So and here is an example. So let's take our previous examples in which you are going to have an offset of the you have a 32 bits address. The offset is 12 bits. So the physical page number is 20 bits. Okay. So now for in a page table, what you need the physical page number, which is this 20 bits. So what about the rest of these, the rest of 12 bits? So for the rest of the 12 bits, you are going to have a bunch of flags, which are used. So you have different use. You can use it in different ways. But here is an example, and this is from Intel architecture. So these are examples about this bits, and we are going to start from the least significant bits. 0 is P. This is present. It's the same as valid. Is the page present in physical memory or not? W, writable. Can you write on this page or not? If it's 0, then it's read-only. U, it's user accessible. Is this page accessible only by user? Okay. PWT, page write transparent. This is related with a cache. Typically, you have caches to reduce the latency to access the data, right? And when you have caches, the question is about how you are going to update the physical memory, the data in the physical memory, right? And there are two ways here we are going to learn, but one way is that whenever we are going to access and we are going to write to the cache and modify the data, we are also going to modify the data in the physical memory. And this is page writes transparent. Page CD is page cache disabled. You cannot cache the pages. It's access, page has been accessed recently. This is used also for caching, right? If it's accessed recently, and the next two is the same, also for caching. You want to know whether the page was accessed recently and whether it's dirty, whether it was written. And the physical memory, associated physical memory was not updated. So you need to know about that. And then you are going, we may decide to page that to, this is, okay, how do I say it? So these 2 bits, the only thing you need to know now, are used when deciding what page to swap out of the memory to make room for new pages. Fundamentally, you do not want to swap up a page of a process which will be accessed immediately. And okay, let me, it's a question. The PCD means, the question is, a PCD means, it's about what PCD means. The PCD means that the page is not cached. And again, the reason you may choose to not cache a page is that, for instance, in multiprocessor systems, multi-core systems, when you have concurrency on the same page, you have a page which is shared to different processes which run on different processors, and they can concurrently access that page. And if you want to update the page, if it's cached, in each processor cache, then you have a cache coherency problem. And if you want to simplify that problem, if you want to remove that problem, you can say, okay, this page is never going to be cached. Okay. Okay. So example of how to use PTEs. Invalid PTEs is that is again, even this one can imply different things, and the operating system decides how to use these flags. So once, and one we use is that, which I didn't mention, is that the address space is actually not valid, right? It doesn't, is not allocated. But another way is basically say the page direct, it's that page is not in the memory, it's on the disk, right? And in that case, you need it's a trap to the operating system exception. It results into a trap and to the operating system, and the operating system is going to figure out where is the page is stored and is going to bring it to memory. And this is going to be used by the main paging. We are going to learn about that. Another use here is about copy on write for the PTE. So basically, when you fork, remember that the fork, when you fork a process, a fork process, copy actually is a parent process, right? It has everything. And now the question is that, do you want to copy it right away, right? And are you going to copy everything? And it's not smart to do it because, for instance, the code of the process, of the parent process, is the same code you are the child process is going to execute. The code is read-only, so you don't need to copy it. But the same is also true about the data, right? Do you want to copy, to copy the data from the process address space to the child address space? Well, the answer there is that only if the child, ideally only if the child accesses it, right, and writes it, right? So so that's what, so initially when you are going to create, because you want to reduce the overhead to create, to fork a process, the fork process can share the entire address space to the parent process, okay? So the reads are very, the reads are going to the same memory. It's memory efficient, it's fast, right, to fork. And but then the only one you can start doing it is when you write it. So when you write a page, now only now you are going to create a copy of that page for the child, and now the child can write and read from that copy. But as long as you only read, you can read from the same memory, physical memory, which is shared with the parent. Another use case here, it's a zero fill on demand. So say you allocate, say 10 gigabytes of memory, and you want to initialize to 0. Just that initialization can take seconds, many seconds, just to do this initialization. So you don't want to pay the overhead then when you are going to allocation. So instead, what you can do zero fill on demand. So the OS knows that this page needs to be 0, but initially doesn't make them 0. It makes them 0 only when you access that page. And that's perfectly fine because you amortize zeroing it, or even better, maybe, the application is not going to ever touch every byte which was allocated in these 10 gigabytes, right? So it's again, some smart ways to use this PTE. So sharing with multiple level pages. Sorry. Oops. You can see here, you have two processes. You have this, each process has its own page table hierarchy, and the first level page, you can see for each process, it's pointed from you have the page table pointer for, and page table pointer prime for the two page tables, different page tables, first level page tables. And then each of them, they have point to second level page tables. And what you can see here is that some of the second level page tables are shared. And obviously all the pages to which entries in the shared page tables point to are also shared, right? And finally, you remember we started with this solving this problem that the page tables can become extremely large, and if we have many of the entries from these huge page tables are null, so contains no information. And we said that the two-level page table is going to solve that, address that problem, or at least alleviate that problem. And here is an example. So if you remember, this is an example, and let me just try to go back here. So this is a previous example. So this is an example in which you are going to have, if you can see, this was a one level table. So you have, I think, 32 entries. Many of these entries are null, right? So, and this is a corresponding example. Let's see. This is a corresponding example, so you can see and you can count. You have much fewer, you require less storage for storing these page tables, right? And certainly you have much more fewer null entries. Okay. So let's continue. We have just a few more minutes, and this also shows you about how the translation is done. So in this particular case, we have for the first page level page table, we use 3 bits, for the second level 2 bits, and for the offset 3 bits. Okay. So in the best case scenario, total size of the page tables is the number of pages used by the program in the virtual memory, unlike the previous case in which the number of pages was the one available in the physical memory. The price to pay here is that you have one more additional memory access, right? Because you need to index on both page tables at both level. How about you know, about segments and pages, right? This is another way to do it, right? It's like we have two-level tables, but another way to solve similar problems is to have to combine segmentation with paging. So in this case, again, you have the address is split into 3 fields, but the first field represents a segment number. The second field represents a virtual page number within that segment, and then you have the offset. Okay, so it's a very similar approach. It's again here. What do you need to save and store when context switching? You need to store the segment table. You need to store the page table for that process. How do you share the data across different segments when you have this both segments and paging? It's the same, very similar way, right? You are going to have from 2 different processes. They can share the pages by simply having the base by sharing the segment, right? If you want to send a bunch of pages, you are going to put all these pages in the same segment, and you are going to share the segment. Okay, very simple. So let me do this one last slide, and then I'm going to stop here. So when you have multi-level translation pages, what are the pros and cons? Okay, so the big pro is that you get to is much less space for the page tables, right? That's it. The paging in themselves, they have the big advantage that it's fixed size. So they retain the simplicity. You have no external fragmentation, you have only internal fragmentation. The cons is that the page tables can be huge because they need to be continuous, because you need to index into them. And therefore, you need to have multiple level of tables in order to get the memory allocation, to get efficient memory allocation for the page tables. But the big problem is that now you need to have multiple lookups for translation, because you need to have a lookup for each level, for each page level. So let's stop here, and again, please attend Nathan's lecture on Thursday, and I'll see you next Monday. Thanks. So we are done. Let me just stop recording.